looks like everybody's here that's going to be here. For anyone who hasn't already seen it, the first set of homeworks are posted, week 1 and week 2. They will be due September the 1st or 2nd. It's a Thursday at 11:59. Generally, this is going to be the trend for all of the homeworks. They'll all be due on a Thursday at about 11:59, or not at about, at 11:59. And so far as the exams are concerned, because that's the next obvious question, when will exams be? Generally, I'm going to have them at the end of the week, because who wants to spend the weekend dreading that upcoming exam on the following Tuesday or Monday, right? So all of your exams will also be, generally speaking, on Thursdays. There are 4 of them, plus the final. What else am I forgetting about that? I think that's all the announcements I had for today. Having said that, let's get into section 1.2. So starting off, section 1.2 is really just about this idea of graphs, how we sketch them, how we interpret them, et cetera, et cetera, et cetera. So I thought we'd start with an example of a graph. Let's say we were given this equation here, 7 minus 3x. And we wanted to graph it. How would we go about graphing that? Any thoughts? Well, it's already in that form, right? So you're right. Starting off in that y is equal to mx plus b form. Yes, sir.
And you just put values next to the x.
Yeah, absolutely. That is definitely one way we could go about it. We could go about it with a tabular approach. So let's start off with a table of x and y values. If x is, say, -1, then that becomes 3 plus 7, which is 10. If x is 0, then it's just going to be 7. And if x is 1, then we're going to get 7 minus 3, so 4. And if x is 2, we're going to get 7 minus 6, so just 1. Now notice, it doesn't look like it in this form, but what we have are order pairs, right? We have the order pairs, -1, 10, 0, 7, 1, 4, and 2, 1. And after yesterday's lecture, we know we can go ahead and just plot these on a graph. When we do, we're just going to get a straight line, right? But this is really just review at this point. Cleaning up whatever needs to be cleaned up from algebra. So looking at this equation, we know this is the equation of a line. And this should plot a line when we graph it, right? So going through, checking out a quick table, they go from 0 to 4. And they plot it and find exactly what we just predicted. It's a line. Nothing revelatory here, nothing groundbreaking. Like I said, this is just going to be a review for the first couple of days. Or for the first day or two. So once we plot these, we'd obviously want to say, what's the most appropriate line to connect these? And that's what we're going to plot, right? We're going to say that that line represents our function or our equation. Now, in the case of x squared minus 2, we can't just assume, or we can't plot this with just a straight line, right? This is going to be a parabola. And we'll see that once we start plotting this. Okay, is -1, 0, 1. -1 squared is 1. Minus 2 is going to be -1. 0 squared is 0. Minus 2 is going to be -2. 1 squared is 1, so we're going to get -1 again. 2 squared is 4, minus 2 is going to be 2. So when we plot this, it's going to look something like this. Right? But notice here, it's not going to be a straight line. We've got a bit of an arc to it. So using a rough estimate of straight lines, we can go ahead and start anticipating what that curve might look like, right? It'll look something like that. In general, this is how we're going to go about sketching graphs. Again, this should be mostly reviewed to everyone. So checking out what the book did, what our solutions suggest, they go from -2 to 3, but they generally are going to get that same pattern. That sort of arc. But then after approximating it with straight lines, they curve everything out and say, all right, look, it's a parabola. Ooh, exciting, I know. The way everyone wants to spend their first 5 minutes of the morning, right? Sketching graphs. This is so much fun. I promise this class will get more interesting as we go on. Or at least I think it will. So from here, a natural question might occur, how can we make this process easier on ourselves? One way we could do that is we could go about finding our x and our y intercepts. So x-intercepts are going to be found by setting y equal to 0. And y-intercepts are going to be found by setting x equal to 0. So if we wanted to look at this problem and find our x and our y-intercepts, we've got x squared minus 2. We're going to find our x-intercept by setting y equal to 0, which tells us that 0 is going to be equal to x squared minus 2. Solve for x. We're going to add 2 to both sides to get 2 is equal to x squared. And then we're going to take the square root of both sides, right? We're going to get plus or minus the square root of 2 is equal to x. So this is where our graph is going to go through the x-axis, right? When y is equal to 0, then x is equal to plus or minus the square root of 2. Now, in the case of y-intercepts, we're going to set x equal to 0 and solve for y. That's straightforward. That's just going to be -2, right? So what does all of this tell us? This tells us that our x-intercept is going to occur when x is equal to plus or minus the square root of 2, which means y is going to be 0 when x is equal to either of those values. And our y-intercept just means that when x is going to be 0, y is going to be -2. And really quickly, when we check out our graph, eyeballing this, this is about negative square root of 2. That's negative 2. And that's square root of 2. So it jives with what we just found over here, right? Our x-intercept, where we're going through the x-axis, was in fact at plus and minus negative 2, or negative square root of 2. And where we go through the y-axis, it is in fact at y equal to negative 2. Make sense? Now, with that in mind, there's a bunch of different ways we could be intercepting our axes. Start off with, we could never intercept our axis. This actually happens a lot. And we're going to be talking about circles in a little bit here. But we could have a case where we just never intercept either axis. We could have cases where we intercept the y-axis multiple times, but not the x-axis. We only intercept the x-axis once. We could have the reverse case, or we could have the case where we only intercept one axis. Notice when we go through the origin, we consider that an intercept of both axes, right? And that makes sense because the origin is where the axes intercept each other. So if you go through the origin, you have to go through both axes. So let's say we wanted to find the intercepts of A. How would we go about doing that? What are we going to do here? Okay, absolutely. Set x equal to 0, and that's going to let us find which intercept.
Y.
Y. Okay. Let's do that really quick. Should just keep my chalk over here. Okay, so we're saying let x be 0 to find the y-intercept. Well, if that's the case, then we're going to have 0 cubed, which is 0, minus 4 times 0, which is also 0. So y is just going to be 0, right? Nothing revelatory there, nothing too exciting. Now, in the case of finding our x-intercept, we're going to set y equal to 0, right? Okay. When we do that, we're still left with x cubed minus 4x. So what should we do next? Any thoughts? Factor, exactly. So the first thing we can factor out is that x, right? Since both terms share an x, let's go ahead and factor that out. When we do that, we're going to get x times the quantity, x squared minus 4. And I claim this can be factored. How can it be factored? Does anybody know?
Reverse FOIL.
Yes, reverse. You could reverse FOIL it, yes. So what would that come out to be?
X plus 4, or no, x plus 2, x minus 2.
Absolutely. Once we go ahead and factor this out, we're going to get that this is x times x minus 2 times x plus 2. So in order for y to be 0, x has to be 0, or this factor has to be 0, or this factor has to be 0, right? Makes sense? Because what we're saying is we've got 3 things being multiplied together. And the only way you can ever get 0 out of multiplication is if one of the things you're multiplying with is 0. But we've got 3 things we're multiplying. So we have 3 possible cases to multiply by 0. Really quickly, I'm going to erase this. this tells us that either x is equal to 0, x minus 2 is equal to 0, or x plus 2 is equal to 0. Well, x equal to 0, that solves itself. We don't have to do anything here. But these two, we do. We do have to rearrange our terms. When we do that, in this second case, we get x is equal to 2. And in this third case, we get x is equal to negative 2. So our x-intercepts are going to occur at x equal to 0 and at x equal to plus or minus 2, right? And we saw that our y-intercept is going to occur when x is equal to 0. So let's check these out really quick. Looking at this first case, when we set y equal to 0, we do in fact have to factor these. And when we factor and we get that our solutions are x equal to 0 and x is equal to plus or minus 2. Now to find our y-intercept, we set x equal to 0, and we find the same thing, except here y is going to be equal to 0. So our x-intercepts are what we predicted, and our y-intercepts are what we predicted. And what this allows us to do is anticipate what this graph is going to look like. We know we're going to have to go through the x-axis 3 times and the y-axis once. So if we go ahead and graph just those 3 points, we can automatically assume that this is going to look something like a cubic as far as the graph is concerned, which is exactly what we had, right? It was a cubic. So by finding these x and y intercepts, we can anticipate what our graph will look like, which will help us narrow in what values we need to consider. Imagine trying to graph this without looking at your x and y intercepts, right? How many points would you need before you'd actually figure out what this graph might possibly look like? If you were just sitting with values between -1 and 1, you might assume that this graph looks linear. You'd be wrong, but you might assume it, and it'd be reasonable, because through here, it kind of does look linear, right? So this is the point of using x and y intercepts, to kind of work around built-in assumptions we might have just from plugging and chugging in values. Make sense? Having said that, as the other example, here, we're going to go about it the exact same way, except our equation's written backwards, right? It's written in terms of x is equal to something instead of y is equal to something. But we're going to go about it the same way. We're going to set x equal to 0 to find our y-intercept. We're going to set y equal to 0 to find our x-intercept. Cool? So our y-intercepts should be plus or minus the square root of 3, right? Except we'll never be able to get, let me unsay what I was about to say. I was about to say we can never get that negative square root of 3, but we can here. So our y-intercepts are going to be plus or minus square root of 3. And our y-intercepts are plus or minus square root of 3. And our x-intercepts are going to be -3, right? Makes sense what I mean? And that's in fact what we get. X-intercept -3, y-intercept square root of 3, negative square root of 3. Now, you'll notice I'm referring to the non-zero part of our intercept. That's just because when talking about the x-intercept, we know y is going to be 0. When talking about y-intercept, we know x is going to be 0. So it doesn't make sense to go ahead and say that it's a redundant statement at that point, right? So it's okay just to be like, yeah, your x-intercept occurs at -3. We'll understand what you mean. Make sense? For whatever it's worth, this is what that graph looks like. You can see why knowing that you'll have 2 y-intercepts might be helpful. Because if we didn't know that, we might just consider the top half of this, because that would be a square root. Just the top half of it would. And the bottom half would be a negative square root. So without going ahead and finding these intercepts, we're also prone to mistakes just from what we commonly experience. Having said that, let's move on to circles really quick. The basic anatomy is such. You've got a center. Amazing, I know. That center we usually denote using HK. We've got a radius. Nothing, again, nothing revelatory here. Now, having said that, a circle is going to have constant radius, right? So we know that in our equations, that value is going to be constant. So using that, what do we think the equation for a circle might be? Well, every point on the circle is going to be r away from the center, right? And our distance formula can be applied here. Since r is going to be represented as the distance, right? It's the distance from the point on your circle to the center of the circle. We know r squared is going to have to be equal to x minus h, that quantity squared, plus y minus k, that quantity squared. And this is just a distance formula, isn't it? So what we're saying is we want to be r away from the center. We want that value to be constant. So let's go ahead and just go back to our distance formula and set d equal to r. Just make that constant. When we square both sides of that, that's going to allow us to make the entire circle. And the reason why is because we don't have negative radius, but we have a value that can be thought of kind of like negative radius. Does that make sense what I mean? How do I want to say this? I'll come back to that thought in a minute. What this is, it's just a application of the distance formula. Saying you have a distance that's being held constant, and you want to find out all the points of that distance away from some other point. Everybody cool with this? And hence we get the standard form of the equation of a circle. So if we wanted to find the equation for a circle with a point at 3, 4 and a center at -1, 2, all we would do is come back to this equation, plug in 3, 4, plug in -1, 2, find out what r is, and then point x and y back in accordingly. Excuse me. Cool this idea? what I'm saying is, we know in our example, we've got an x1 and a y1 that lies in our circle. That's 3, 4. We know our HK is -1, 2. So now, putting all of this together, we're going to get r squared is equal to 3 minus -1, that quantity squared, plus 4 minus 2, that quantity squared. So this is going to come out to be 4 squared plus 2 squared, 16 plus 4, right? Or just 20 is equal to r squared. So the standard equation for our circle is just going to be 20 is equal to x minus -1, that quantity squared, plus y minus 2, that quantity squared. That's it. Does this make sense to everyone? Yeah. Cool. So what we're finding is the equation of this circle right here. We start off by finding the distance or the radius between these 2 points. And then replace r with that and just throw x and y back in. Yeah. So what that looks like, they kind of skip over a step here. They don't explain why we use the radical here. I think it's more obvious to go about it this way, because once we get here, we realize we can go ahead and apply the square root to both sides if we wanted to, or we could just say, I've got r squared anyhow, just leave it as 20. Does that make sense? But the reason why they have r is equal to all this under the radical is because they got to here and took the square root to both sides. Yeah. From there, all we do is plug in that r value again and plug in the corresponding h and k values, or replace the 3 and 4 with x and y. Yeah. Now, the more monstrous form of that equation. We have what's called the general form of the equation of a circle. And if we look at what's happening here, we can kind of make out where this might come from. We're going to come back to just the standard form. We're going to say, hey, look at these two terms. We can expand both of those out. When we do, this first term is going to be x squared minus 2xh minus, or my mistake, plus h squared plus y squared minus 2yk plus y squared. I mean, k squared. And from here, when we rearrange everything, we can get back into that form. So rearranging, we get x squared plus y squared minus 2xh minus 2yk plus h squared plus k squared. Now the question is, where does this a come from up here? All they're saying is you can take any circle and scale it. If I were to take this and multiply by a, down here, we would have an a that would distribute back through. Does that make sense? So this general form actually comes from the standard form. It's just the standard form rewritten. And the way we go about finding the standard form from the general form is by completing the square. Having said that, if you're not sure how to complete the square, if you don't remember how to, check out the algebra notes. I'm trying to remember where exactly in the algebra notes, in the algebra review notes, I have them. Let me look at that really quick. In the algebra review notes, I think it's like day 11. Yeah, it's right around day 11 that you're going to find completing the square. These are inequalities. I don't remember where exactly in these notes, but they are in them. So if you needed the review, by all means, check out those notes. This is not your class, that is mine. Stop share and share again. So looking at an example right away, what do you notice? You could almost factor out a 4 from every term, right? Almost. In fact, if you could find some way to rewrite this to be a multiple of 4, then you could factor out every 4. Does that make sense what I mean? So really quickly, just to give you an idea of what this whole process will look like. First, right away, go ahead and divide out that 4. When you do, everything but that very last term, it's going to reduce pretty nicely. From here, you're going to want to complete the square. You're going to want to complete the square by first grouping these terms, saying, all right, I've got things with like values. I've got my x's and I've got my y's. I want to collect these together. And you're also going to want to say, This thing doesn't have an X or a Y. So there's no obvious way of grouping it with the things that have X's or with the things that have Y's. So let's just go ahead and push that off to the side. Let's remove that from our part of the equation by subtracting it out, right? Now from here, you're going to want to complete these squares, each of these individual squares. But notice that requires you to add something into the equation. So you're going to have to add that to the other side as well. You're going to have to say, all right, I'm going to add 25 over 4 to the left side. So that means I need to add 25 over 4 to the right side. I need to add 4 to the left side. So I need to add 4 to the right side. From there, you want to simplify those two terms, those two groups of terms, and then you want to simplify the right side as well. So what we've got in this case is a circle of radius 1 centered at x equal negative 5 over 2 and y equal to 2. Yeah. I think I've got the picture on the next slide. I do. So we've got a radius of 1 and a circle centered at negative 5 over 2 and 2. Now, having said all of this, there is an important point to make. You can't get a negative number for your r squared. Radius squared can't come out to be negative. Why is that? Why do you think r squared can't come out to be negative?
Have a negative distance.
Yeah. Yeah, and moreover, it requires your radius to be imaginary, right? Because the only way you can square a value and get a negative out is if it's imaginary. So what would imaginary radius be? Really doesn't actually have a meaning. So for that reason, r squared cannot be negative. In other words, we went all the way through this and got -1. It's not a circle. I have no clue what it is, but it's damn sure not a circle. Cool. Having said that, as a fun fact, who thinks imaginary numbers don't exist in the world? Just out of curiosity. Show of hands. If I told you something had an imaginary number, do you think it means anything physically? No? Who says no? Who says yes? It does. Negative or imaginary numbers do actually have meaning in the physical world. In spite of what I just said about the circle and imaginary numbers, you cannot have a circle in the physical world without imaginary numbers having some sort of a meaning. The reason why we call imaginary numbers is because we had already called real numbers real numbers. We're like, well, these aren't real numbers. We need another name for them. Let's call them imaginary. And that's just stuck. Mathematicians for close to the last 200 years or so, a little bit longer, pretty much since imaginary numbers came into their own, mathematicians have hated this vocab of real numbers, imaginary numbers, complex numbers. We've hated it because when talking about imaginary numbers and teaching these subjects, it gives students this perception of they're fake. They don't mean anything. They do. They actually happen all the time. Anyone who might go on to study chemistry or physics, get real comfortable with imaginary numbers because you can't have quantum physics without it. cloud orbitals, etc. All of these things require imaginary numbers. And in that way, they actually do have a physical meaning. You just don't necessarily have an interpretation for that physical meaning in those cases. And complex numbers, for mathematicians, we love those. We get a complex number and we're like, oh yeah, this is meat. Because it's a lot easier to work with than real numbers. So just as a segue, a little bit of a point here, imaginary numbers are not really imaginary. Complex numbers are not really difficult. And real numbers aren't necessarily preferred numbers. It's just naming, and it kind of sucks the way we name these things. But anyhow, getting back into the lecture, points of intersection. Let's say I give you two different equations. I tell you they're intersected. They have some value in common. How are we going to go about solving that? Well, if we say there's an intersection or an intersection between these two equations or functions, what have you, then we know they're going to share values, right? If they're going to share values, we can go ahead and say, let's solve both of them for y or for x and set those two values equal, right? So looking at this equation here, x squared minus 3, and looking at that other equation, y minus 1, or I mean x minus 1, we're saying y is equal to both of those. And then we're saying we want to know when they give us the same point, when they occupy the same point. Well, if they occupy the same point, those y values are going to be the same. So why don't we say, to solve when that happens, set those two equations equal to each other. Their y values are, after all, equal. And then we rearrange our terms so we can solve for x. So what that allows us to do then is say, we know these two things are going to share the same y value. What x value makes that happen? And what that looks like I said, is setting them equal and then working through the algebra to solve for x. So we say, cool, we've got x squared minus 3 is equal to x minus 1. Well, I'll be damned, I can subtract x minus 1 from both sides. I'm just regrouping the terms, right? Keeping constants with constants, x's with x's, right? So this is going to give us x squared minus x minus 2 is equal to 0. And from here, we're just going to have to apply the quadratic formula, right? Or if we can factor it out, we're going to need to factor it out. So this allows us then to solve for x and answer the question, what x value makes it so that these two things have the same y value? So when solving for equations being equal to each other, we're solving something that is actually physically real. It does in fact exist. Who plays basketball? Do I have any basketball players? One? All right. So you and another guy go to I don't know, tip the ball out of the sky, whatever. I'm not a basketball player. I don't know the first thing about basketball. But you and someone else go to grab the ball. It's up in the air. If you're running in straight lines, there is a moment where that ball is where your paths have to intersect, right? And if you wanted to actually solve when that would happen in the physical world, you would use a system exactly like this. You'd say, what's the equation that models those two paths, set them equal to each other, and solve for the corresponding variables? Cool. So all of this stuff that we're going to talk about, it has meaning and it has application. And you do in fact use it on an intuitive level all the time. Having said that, let's keep jumping into these. Actually going to look for, yeah, I'm going to go ahead and jump into supply curve stuff. So I assume since this is a bunch of business students in here, we already know what the supply curve and the demand curve represent, right? Price and the amount of production that we have. Yeah. So when talking about the equilibrium price, what we're literally talking about is when the demand function and the supply function are equivalent. So again, in the physical world, where does this exist? This exists within the business world. What's your equilibrium price? Or your equilibrium point, however you want to put it. It's the spot where your demand and your supply function intersect each other. This class is over at 15, right? Yeah. Cool. So we're going to get through all of this, I think. So having said that, let's say we've got a demand equation and a supply equation for DVD players. For those of y'all who are not old enough to remember, DVDs are what we had before Blu-rays. I know it's been a few years. So if we want to find the equilibrium point, what are we going to do here? So what?
Set them equal to each other.
Yeah, just set them equal to each other. Let's say I got 195 minus 5.8 times x is equal to, so that's our demand equation, is equal to our supply equation, 150 plus 3.2 x. And all we're doing here is saying the price of the demand equation is equal to the price of the supply equation. And now we're asking the question, what x value makes that happen? Cool. From here, we're just going to rewrite everything and solve for x. I would suggest adding 5.8x to both sides and subtracting 150 from both sides. So when we do that, we're going to get 45 is equal to, it looks like what, 9x. Now solving the rest of the way. We get 5 is equal to x. Everybody agree? So we've done the x value that makes this happen. Now we need to find the price that makes that happen. Personally, I like this equation more than I like this equation. But if we want to find the price that makes this happen, we need to plug this x value back into either one of those equations, right? So since I like this equation more, we're going to get 150 plus 3.2 times 5. 3.2 times 5 is 16. So that's 150 plus 16 or 166 is equal to P. So what we've got now is that our equilibrium point is equal to 166. And that's barring any mistakes that I may have made. So checking out these two equations, we got the supply curve, we got the demand curve. Hey, what do you know? They do intersect at the point 166. Yes, sir.
What is the 166 like represent though, like, as far as the price and what?
Yeah, so all this is representing is based on the supply and the demand function when they would intercept each other. So when are they going to compute the same value? One way to think of this is one way to optimize your cells, right? If you're a company and you want to sell the maximum number of goods and get the most benefit out of that, this is one analysis you might want to do along the way. Does that make sense? Like you want to get everything out of your warehouse. You don't want anything sitting down. You want to just get it out fast, right? So your PlayStation, and you decide you want everything gone, but you want to make the most money for everything you sell. This is when that happens. After that point, you've got things sitting in your warehouse. Before that point, you're not making as much money as you could. Make sense? Does that answer your question? Yeah. Cool. So how does this work? Well, it works exactly like what we just did on the board. We set both equations equal to each other because we're saying we know the price has to be the same there. So why not just go ahead and say these two things are the same and solve for the X value that makes that true? So we set those equal. They start off by going ahead and subtracting 150 from both sides and then adding 5.8. I did that all in one stroke. And then divide both sides by 9, and you get 5 is equal to X. That's all great and good, except this doesn't tell you what the price is. It only tells you what the number of commodity items are, right? The number of goods, the unit of goods. So you're going to have to take this value and plug it back into either of those equations. They decided to plug it back into 195 minus 5.8, and they got 166. Notice it doesn't matter which one you used, right? It doesn't matter because you just solved for when they're the same. You solved for the X value that gives the same Y value. So go ahead and pick either equation, put that X back in, and you're going to get the same Y. Cool. So all of these are to say that these are examples of mathematical models. Really all a model is a set of a system of equations that we use to predict or to describe or explain what's happening in the physical world. This has literally dictated your life forever and a day, especially for the last year and a half when everything's been about COVID. 90% of our decision-making has been about mathematical models of how COVID is going to move through the environment and through our societies. So the way these generally work, you've got a bunch of data. So here we've got data of cells. I think this is profit, right? Yeah, cells. All right, so these are cells of different companies for different years. And what they're going to do here is they're going to say, all right, based on this data, we want an equation that approximates what's actually happening here. Once we find that equation, then we're going to use it to project what might happen in the future. So they've got their data, and they're saying, all right, well, Kohl's looks approximately linear. Dillard's looks maybe exponential, maybe a polynomial, but certainly not a line, right? Like it's not just a linear equation. So using least square regressions, they find the two different equations that represent these two graphs. What they're doing is they're saying, find the equation whose line is whose graph is as close to these points as possible. That's what least square regression is. You're basically saying, I want a polynomial that is as close to these points as I can get it. And after applying that model, this is what they find. They say, all right, cool. We've done the analysis. The least square regression analysis tells us that these two equations best approximate our data. In this case, this is Kohl's data. In this case, this is Dillard's. Now, based on this, let's predict what's going to happen the next year. So they go on and they say, based on all of this, what's going to happen next year? This is what we're estimating. So again, when asked, where am I going to use this? How would I use this? Where does this show up? It shows up everywhere. And this stuff shows up all over the place in the business world. If anyone works with quality control, you use this sort of analysis literally daily. If you work with some other part of business management, you might use it once a month to once a year, but you are going to use it. It does show up regularly. I shouldn't say once a year, probably once quarterly. So to get over that hurdle of why am I learning this? Why do I care? It's going to show up. It's going to show up quite regularly. Having said that, there are a bunch of different types of mathematical models that exist. We've got our linear model. We've got a quadratic model. We've got a cubic model. We've got our square root models, our absolute value models, and rational models. I'm sure Hollywood would argue there's no such thing as a rational model, but that's just a guess. Really? I thought that one was funny. Damn, y'all are tough. All right, well, moving on. That's really all I had to say about mathematical models, just some general basic details. These are good things to know. We will use each of these different types of models throughout this class, so get familiar with them. That way, when you look at a graph, you can identify or guess at what it might look like as an equation. Cubic models are going to show up all over the place, as well as square root and absolute value and rational models. We will use quadratic and linear models throughout this semester, but more so these other four. I also suspect we already know what linear and quadratic models look like. So, section 1.3. Section 1.3 begins the good stuff. We're going to start talking about slope. Slope is really just this idea of inclination of a line, right? What slope tells you is we've got some line, how inclined is it relative to what we're looking at? Yeah. Or relative to how we're measuring it. It compares the number of units you go up to the number of units you go across. And it compares that as the ratio over, my mistake, up divided by over. Does that make sense what I mean? Rise over run. We all recognize that the slope of an equation of a line is going to be m. We should also notice from what we were just talking about before with y-intercepts that the y-intercept is going to happen when x is equal to 0. So that means the y-intercept of the equation of a line is just going to be b. Yep. But there are a couple exceptions here. In particular, we have the exception when x is equal to a constant. That's just an undefined slope. We don't have a definition for that. Well, we do have a definition. We just call it undefined though. So based on that, if we wanted to, we could go through and write or draw the graph of each of these equations, right? So out of curiosity, what is B going to look like? Yeah, it's going to be a horizontal line. What about A? Well, the graph of A is going to have to go through the point 0, 1. It's going to have a slope of 2. So it's going to be inclined kind of steep, but not too terribly steep. And it's going to have to, like I said, go through the point 0, 1. What about C? Well, to find C, we're going to have to subtract x from both sides, right? Which means the slope is going to be -1, because you're going to have y is equal to 2 minus x. So we have a slope of -1, and the intercept is just going to be 2, 0. I mean 0, 2. Agreed? So checking out that first graph, we've got a slope of 2. We go up 2 units for every 1 unit over we go. Checking out B, it was in fact that straight horizontal line. It has a slope of 0. So another way to think of this is it's the equation 0x plus 2, right? And finally, that last equation, once we rewrite it, we're going to get a slope of -1 and a y-intercept of 0, 2, which is in fact what we see. We intercept the y-axis at 0, 2, and we have a slope of -1. So for every unit over we go 1 unit down. Yeah. Now, we could, if we wanted to, talk about this in a more physical sense. Let's say we're building a ramp so that somebody can have access to a building. We want to talk about the inclination of that ramp. Well, in this case, the first thing we're going to have to do is convert this back into inches or into feet. Agreed? Because we've got 22 inches up for every 24 feet over. So, first thing, let's turn that 24 feet into inches. Multiplying by 12. Anybody have a calculator? Because I am not doing that in my head.
144 times 2.
24 times 12.
12 times 12.
144.
Yes. Times 2. Oh, you're right. Good catch. Good catch. This brings another point. If you can find tricks like that to help do the arithmetic, definitely do that. So his point here is that 24 can be broken up into 2 times 12. Well, we know that 12 times 12 is 144. So this is going to come out to be 288. Good catch. So this is going to be 288 inches. Now, we're just going to want to divide the rise by the run. So that's going to be 22 divided by 288. So 11 over 144, which is less than 1 over 12, right? Because 11 divided by 12 is just 11 over 12. 144 divided by 12 is 12. So this is going to be this is less than 1 divided by 12, which is less than the slope of a wheelchair as recommended. Cool. So the whole point of this is just to get us used to the idea of slope again, to kind of get us into the groove of understanding what it even means, what we're talking about when measuring slope. It is a literal physical quantity. I'm trying to think of a decent example that I can point to. Without doing anything, I don't have one off the top of my head. So just really quickly looking at what the book's solution is, they rewrite slope as the vertical change over the horizontal change. They recognize that it is in fact less steep than what's recommended. So one way we can think of slope is as a rate of change. What slope is telling us is for every change in x, how does y change? Or for every change in y, how does x change? We can think of it that way, right? So if we wanted to describe the practical significance of an equation, we can think of this 25 as a ratio of change. So 25 represents the change in cost for every unit of product added. Does that make sense? Yeah. Having said that, the general equation for the slope of a line is just going to be the change in x, or the change in y divided by the change in x. I started to say that backwards again. But we have to hold that x does in fact change, right? Now, you'll sometimes see me write it with these deltas. That's because all delta means is change. Or at least to mathematicians and physicists and engineers and chemists and to the STEMs. Delta means change. So we'll use delta y to represent the change in y, or delta x to represent the change in x. Now a question might occur, does order matter? Could I swap y1 and y2? The answer is yes, if you swap x1 and x2. but only if you swap x1 and x2. So the way you take the change of y has to be the same way you take the change of x. Is everybody cool with this? Yeah. In other words, these have to agree in where the points are coming from. So if I say, I'm going to take the first point and subtract the second point from it to find my change in y, then I need to do that for my change of x. I cannot change the orders across the division. Cool? Across the fractions. Yeah. So if we wanted, we could go through and find the slope of the line that passes through each of these points. Checking this out really quick. We've got the point -2, 0, and the point 1. We want delta y over delta x. So that's going to be 1 minus 0 over 3 minus -2. So this is going to be 1 over 5, or you can rewrite it as 0.2. So really quickly, looking at the solution as the book provided it, 1 over 5. So this isn't too terribly crazy. It is easy to overthink, so please keep that in mind. Do not overthink these things. Math is definitely one of those subjects that we all have, where we're all prone to overthinking. So be mindful of that. Don't let yourself overthink this stuff. Notice in this last case, we had the points 3, 4 and 3, 1. They share the same x value, so they're going to be just the vertical line, right? And vertical lines, we said, have a slope that's undefined. And that's what they're saying here. So this brings us to another point. There are several different ways to rewrite or to write the equation of a line. If given a set of points, we could use point slope form to find the equation of a line. If given just the line and an intercept, or the slope and an intercept, we could use slope intercept form. And then there's just the general equation of a line as well. So what this allows us to do is to say, I've got x1, y1, and x2, y2. This tells me what m is. My slope, right? So from here, I can just plug in either my set of x1 points, my set of x1 values, 0.1 values, I should say, or my set of 0.2 values into y1, x1. It doesn't matter which set of points you use can use either set. Is that cool? So if I told you that a line had a slope of 3 and passed through a particular point, well, we already know the slope now. And we know it has to go through this point. So we can just plug all of this in and not have to worry about it. Whereas if I just told you two different points, we'd have to go through that process. Yeah. So we know it has a slope of 3. And it has to go through the point 1, -2. We're told what it's going to look like. When we're done, our solution should come out to be y is equal to 3x minus 5 when we put it into slope-intercept form. So using point slope form, we start off with m is equal to 3, x1 and y1 is 1, -2. So we have 3 times the quantity x minus 1 is equal to y minus -2. Rewriting everything, we can now simplify and put it into slope-intercept form. Having said that, before I let y'all go, I just wanted to show y'all some generally, or the different equations of lines. You got your general form, your vertical line, your horizontal line, your slope-intercept, and your point slope form. Having said that, y'all are free to go. I'll stick around if y'all have any questions.